Heat is the transfer of energy. Now that we're studying heat, we can include it as part of our energy model. Remember, work is a transfer of energy. Kinetic energy is the energy of motion. Gravitational potential energy is the energy related to your position near the Earth. Elastic potential energy is related to the energy of a spring. And Q is our new energy of heat. So these are our different types of energy and energy transfer. This example says you push a 2.4 kilogram book 0.85 meters across a level table at a constant speed. If the coefficient of friction between the book and the table is 0.25, how much heat is dissipated? So in our energy model, this is how this would look. We would, as part of our system, have the book, the table, and the Earth. So work in the form of friction is being transferred into our system, and work is also transferring energy out in the form of heat. So we've got work equaling the heat. And so since our work is the force times the distance that we apply onto the book, that would equal the heat that we get out. Remember, our force there is due to the friction. And we remember that the force of friction is mu times the normal force. But in this case, we know that the normal force, since it's just on a flat surface, is the mass times gravity. So the normal force is just the mass times gravity. So in this case, if I plug in for my force of friction, I get mu sub k mg times d is equal to Q, which is my heat. The internal energy is the sum of the energies of all the molecules in a substance. Because it is a type of energy, or because it is energy, its units is in joules. So an example would be like in this piston, we take all the molecules and add up all their different energies, specifically their kinetic energies, we can figure out the total internal energy. Temperature is related to the average kinetic energy per molecule of a substance. Its symbol is T. The units can be in either degrees Celsius or in Kelvin. And remember that Kelvin can be converted from Celsius by adding 273 to Celsius to get the Kelvin temperature. An interesting thing to note, two bodies can have the same temperature, but do not necessarily have the same internal energy. Take, for example, a cup of boiling water and an entire iceberg. The iceberg can have more internal energy because it's got a whole bunch of particles with really low velocities or low energies, but because there's so many of them, it would have more internal energy than does the cup of boiling water. Linear thermal expansion is one of those equations that needs to be memorized because it shows up on the on the multiple choice part of the test. The linear thermal expansion equation basically says the change in the length of an object depends upon the coefficient of linear expansion, the original length of the object, and the change in temperature. An example of this would be this example here that says how much longer will be a 3-meter section of concrete when the temperature increases from 25 degrees Celsius to 38 degrees Celsius. So we simply put into our equation the linear thermal expansion equation. Alpha is the coefficient of linear expansion. Again, that's going to depend upon the object. In this case, concrete has a linear thermal expansion of 12 times 10 to the minus 6 and the units are 1 over degrees Celsius, times the original length, which is 3 meters, and the times the change in temperature. So the change in temperature is always final minus initial. So 38 degrees Celsius minus 25 degrees Celsius gives us a certain value. I want you to calculate that out, and the units obviously here are going to be in meters. It says to increase the whole or the inner diameter of a metal ring, do you heat it or cool it? So let's instead of looking at an actual ring, let's look at tiles and break down the tiles into a bunch of squares. So here's the center of the squares. If we heat each of the squares and they each increase by the same amount, notice that the inside increases when we heat it. So we want to heat the metal ring to increase the inner diameter. Rate of heat transfer is the symbol for it is H. Its units are in joules per second. It's solved by using this equation. This is the equation that you need to memorize from the equation sheet. However, because the rate of heat transfer H is equal to Q over T, we probably are better off rewriting this equation this way, so that H is equal to Q over T. And if we have to solve for Q, because remember heat is very important, because it's a type of energy, Q therefore is K times A delta T over L times T, the lowercase t, which is the time. Okay, so the rate of heat transfer basically tells us how fast this heat is going to transfer from a region of high temperature to a region of low temperature if I know the area of an object and its length. Let's look at this example. It says normal body temperature is 37 degrees Celsius. Excuse me. If heat travels through 0.030 meters of fat, which has a thermal conductivity value of 0.2 joules per second meters degrees Celsius, and reaching the skin, which has a total surface area of 1.5 meters squared and a temperature of 34 degrees, what amount of heat reaches the skin in half an hour? So we can simply plug into our heat equation here. Again, it's solved for heat. Our thermal conductivity value is 0.20 joules per second meters degrees Celsius times our area, which in this case is 1.5 meters squared, times our change in temperature. So we always go final minus initial. In this case, the final temperature is 34, the initial is 37, and then I divide that by the length of the object, which is 0.030 meters. Now, I also have to multiply times t. My value for time is going to be 30 minutes, but I kind of convert that by multiplying it times 60 seconds in 1 minute. So I got to multiply that whole value times that. I end up with a negative 61,200 joules. Now what we're going to do is we're going to do a little chemistry review. We need to remember what the molecular mass is, and if you haven't had chemistry, we'll get this from the periodic table. The molecular mass is the sum of the atomic masses of the atoms in a molecule. So what you need to do is you need to get a periodic table. There's one on the front cover or back cover of your physics book, somewhere in your physics book. And what you have to do is you have to look for the values in the periodic table that give us the atomic masses. So it says calculate the molecular mass of water. So we know water is made out of 2 molecules of hydrogen and 1 molecule of oxygen. So to calculate its molecular mass, since there are 2 hydrogens, we take 2. If you look on the periodic table, now I've got a really precise table that tells me that its value is 1.00794 U. The U stands for atomic mass units. Plus 15.9994 U, and that gives me a value of 18.0153 U, which is again in atomic mass units. Another thing we have to know is Avogadro's number. It's a really big number, 6.02 times 10 to the 23rd, since we're going to be dealing with gases, and there are a lot of molecules and even a cubic liter of gas. We have to use a really large number to represent all those molecules. So Avogadro's number is 6.02 times 10 to the 23rd. 1 mole of any substance or anything at all is equal to 6.02 times 10 to the 23rd. So when I refer to 1 mole of a particular particle, that's really 6.02 times 10 to the 23rd of those particles. Now, the molecular mass, big M, is the mass in grams of 1 mole of a substance. Now, be really careful here, because in chemistry, they define this in chemistry in grams, but remember, we use kilograms. So whenever you get the molar mass, that has to be converted to kilograms. The molar mass and the molecular mass are the same number with different units. So, for example, the molar mass of H2O is the same as the molecular mass. The value is 18.153, but it's in grams. So, 1 molecule, this value up here, is the mass of 1 molecule of H2O in these units called AMUs. If I got 1 mole of H2O particles, if I got 6.02 times 10 to the 23rd H2O molecules, and I were to figure out their mass, it would be 18.0153 grams. But remember, because in physics we use kilograms, that would be equivalent to 0.0180153 kilograms. Now, the kinetic theory of gases. Please read these 5 important facets of the kinetic theory of gases. Understand them, but don't memorize them. The ideal gas law, there are 2 versions of the equation. They essentially mean the same thing, just depends on which equation is more convenient for us. For the most part, we will almost always use that equation. We'll use this equation when it's more convenient for us, when particles are given to us in the number of molecules. For the most part, we're given our problems as a number of moles. The P stands for pressure, the V stands for volume, the T stands for temperature. The N, lowercase n, stands for the number of moles, uppercase N stands for the number of molecules, R is a gas constant, and K sub B is Boltzmann's constant. Let's continue our study of the ideal gas law by solving this example. It says, what is the temperature of 1 mole of an ideal gas when the pressure is 1.5 times 10 to the 5th pascals? The gas is contained in a cylindrical piston with height 0.2 meters and diameter of 0.1 meters. So this is the height, and the diameter is 0.1 meter. So the equation again that we'll use is PV is equal to nRT. But we want to solve this for the temperature at this particular state. So that's what what one version of the ideal gas law looks like when we solve it for temperature. So the pressure is given to us as 1.5 times 10 to the 5th pascals. We need to multiply that times the volume. You need to know how to find the volume of a cylinder. It's base times height. The base is the area of the circle, or pi r squared. So pi times 0.5 meters. Since the diameter is 0.1 meter, the radius must be 0.1 0.05 meters. We're going to square that and multiply that times the height of 0.2 meters. The number of moles is given to us as 1 mole, and the gas constant is 8.31. This gives me a value of 28.4 Kelvin, which is actually a very low temperature. Now, for solving problems where we want to change states, we'll use one of these two equations. The equation on the left or the equation on the right. Because we're dealing with moles, we're going to use this equation. Notice it says if the variable is constant, leave it out of the equation. So in this example, it says for the problem above, the pressure increases to 2.0 times 10 to the 5th pascals. If the temperature remains constant, what is the new volume? So we're solving for the new volume, V2. They're saying the temperature remains constant. So T1 and T2 are going to remain the same, so they cancel out in our equations. We're not told about any change in the number of moles, so we're going to make the assumption that we're solving that, or our number of moles is going to remain constant. So my new equation just becomes P1V1 is equal to P2V2. Solving that for V2, the equation becomes V2 is equal to P1V1 over P2. In which case, we would get 1.5 times 10 to the 5th pascals times our volume again, which we said was pi r squared. Oops. Pi r squared. Let me erase that. Pi r squared. And the r was 0.05 meters squared times the height of 0.2 meters divided by the new pressure of 2.0 times 10 to the 5th pascals. So that comes out to a value of 0.00118 meters cubed, because that's the units for volume. Internal energy. Internal energy is solved using this equation, 3/2 nRT. So it's really important that this needs to be memorized. Make sure you memorize that equation. It says, what is internal energy of 2 moles of the gas above? So what we would do is we would plug into the equation U is equal to 3/2 nRT, where N would be 2 moles, R would be the gas constant of 8.31, and the temperature that was given to us was, or is, 28.4 Kelvin. That's actually what we solved for. And that gives us a value of 708 joules. Okay, now what we're going to do is we're going to look at how to calculate the RMS speed. When we calculate the RMS speed, remember we always use Kelvin. We use this equation here when we have mu, or we can find mu, the mass of one particle or one molecule. We use this equation when we have big M, which is the molar mass, and we need to have that in kilograms. So, for example, when we solve for the equation on the right-hand side, let's solve this problem. It says, what is the RMS speed of O2 oxygen at 300 Kelvin? So, what we would do is we would take the equation 3RT over the molar mass. So, we would take 3 times the gas constant, 8.31, times the temperature of 300 Kelvin, and we would need to find the molar mass in Kelvin, in kilograms. since we're talking about O2, and we can find that the periodic table says that, and I'm going to use a less precise periodic table in this case. 16 would be the molecular mass on this particular table. And 2 times 16U gives me a value of 32U. So the molecular mass in that case would be converted to 32 grams. But again, our equations are written so that we have to use kilograms. So I'm going to convert that to 0.032 kilograms. And that's the equation that I'm going to use here, or that's the value I'm going to use here. So 0.032 kilograms, excuse me, gives me a value about 480 meters per second. Okay. Now, in using the other equation, I'm going to use this equation now. I've got to use the square root of 3 times K sub B, which is Boltzmann's constant, times the temperature, divided by mu. Now, this value of mu is actually the mass of one molecule. So, mu is the mass of one O2 molecule. So here's what I have to do. I take my 32 grams, I got to divide that by 6.02 times 10 to the 23rd molecules. Molecules. And I find that per molecule, I get 5.32 times 10 to the minus 23rd grams, which is actually equal to 5.32 times 10 to the minus 26 kilograms, because I got to convert from grams to kilograms. So this is the value that I will be using in my equation. So to set this up, I've got the square root of 3 times Boltzmann's constant, which is 1.38 times 10 to the minus 23rd times 300 Kelvin, divided by the mass of one molecule of oxygen, which we found to be 5.32 times 10 to the minus 26 kilograms. And that answer also comes out to be about 480 meters per second.